Hi everyone, I am Dr. K. Kritika, Associate Professor, Department of Mathematics, K.S.Rangasamy College of Technology. I am going to explain the principle of mathematical induction from combinatorics from discrete mathematics. Let P of n. So what is mathematical principle of mathematical induction? So here we consider P of n be a statement or proportion involving for all positive integers n. So here there are two steps. Step 1 is basis steps. Second step is the inductive step. So in this basis step, we are going to verify P of 1 is true. Inductive step, if we consider P of k is true. So using that, we are going to prove P of k plus 1 is true. So here I am going to explain some problems related to this mathematical induction. So the first problem is using mathematical induction, prove that summation I is equal to 1 to n I square. It means 1 square plus 2 square plus etc. up to n square, which is equal to n into n plus 1 to n plus 1 divided by 6. So let the solution, the first step of the solution is let P of n is a given proof. 1 square up to etc. n square is equal to the given result n into n plus 1 to n plus 1 by 6. Here n is a positive integer. So the step 1 is basis step. So in this step we are going to verify P of 1 is 2. So to verify this, just be replacing n by 1 in both sides. So here n is equal to 1 means 1 square. So left hand side is 1 square. So in this right hand side also we are going to put 1. So it is already getting a 1. So 1 is equal to 1. Therefore P of 1 is 2. Now we move into the second step. It is called the inductive step. So in this inductive step, first we assume that P of k is true. So using this we are going to prove P of k plus 1 to 1 is true. So P of k means just here in the given result just be replacing n by k in both sides. So we're getting this, we consider this is equation number 1. So to prove P of k plus 1 is true. So to prove this result, we do one thing, just adding k plus 1 square whole square on both sides in equation number 1. Comma we have 1 plus 2 square plus etc. k square plus we are adding this k plus 1 whole square is equal to, similarly we are adding in the right hand side also. So here the first one is a fraction, another one is a normal term, so we cross multiply. So here we cross multiplying means we getting this and we expand this second bracket. So here we taking 2k is outside, so k plus 2, then here 3 outside, 3 into k plus 2. So we getting this. So here therefore P of k plus 1 is true. So by the prime principle of mathematical induction, we can write it as 1 square plus etc. n square is equal to n into n plus 1 to n plus 1 by 6. So now the second problem is prove that 8 power n minus 3 power n is a multiple of 5, which is slightly differ from the previous problem. So here let P of n be a proportion that 8 power n minus 3 power n is a multiple of 5. So in step 1 we take here n is equal to 1. So 8 power 1 minus 3 power 1, it means 8 minus 3, which is equal to 5. Obviously we say that this 5 is a multiple of 5. So P of 1 is true. So step 2, inductive step. So here we are going to assume P of k is true. So assume that P of k is true means just here in the given problem in P of n, just we replacing n by k. So P of k is 8 power k minus 3 power k is a multiple of 5. It is in wordings. So now we are going to write the notation form. So multiple of 5 means we can write it as 5 into m or 5 into n. This is our choice, but here m is an integer. So we can write it as 8 power k minus 3 power k is equal to 5m. So m is an integer. So using this, we are going to prove P of k plus 1 is true. So P of k, 8 power k in the given P of n, just we replacing n by k plus 1. So 8 power k plus 1 minus 3 power k plus 1, which is equal to, we split the term 8 into 8 power k minus 3 into 3 power k, which is equal to, so here the first term is 8 into 8 power k. So we can write this a is 5 plus 3. So 5 into 8 power k plus 3 into 8 power k minus 3 into 3 power k. So in this second and third term, 3 is common. So we take it outside 3 from second and third term. So the term is 8 power k minus 3 power k, which is nothing but equation number 1. So in this step, we are putting 5m. So 5 into, so here also 5 exists, here also 5 exists. So we can take 5 outside. So 8k plus 3 power m. Actually, simply we say that it is a multiple of 5. Therefore, P of k plus 1 is also true. So hence the proof. Then third problem is, by the principle of mathematical induction, prove that n cube plus 2n is divisible by 5. So here also we consider the given statement. It means n cube plus 2n is divisible by 3 is p of n. So in the basis step, as usual, we take p of 1 and we prove that p of 1 is true. So here 1 cube plus 2 into 1, it means 3. Definitely this 3 is divisible by 3. Therefore p of 1 is true. So in inductive step, assume that p of k is 2. It means replacing n by k. So k cube plus 2k is divisible by 3. So now we are going to write it in a notation form. So if any term is divisible by 3 means automatically we say that it is a multiple of 3. So we can write it as k cube plus 2k is equal to 3 into m. So to prove that p of k plus 1 is true. So here in this step just we replacing k by k plus 1 and we apply a plus b whole cube formula and you expand this. We getting this term. And from the second, so here from the third, fourth, fifth, we take 3 outside. Then here also 3 this first and second step k cube plus 2k, actually which is nothing but by using equation number 1, this is nothing but 3m. So here 3 is common. So we take 3 outside. So we say that it is a multiple of 3 or we say that it is divisible by 3. Therefore p of k plus 1 is true. Therefore, by the principle of mathematical induction, the term n cube plus 2n is divisible by 3 for n is greater than or equal to 1. So now we move to the fourth problem. Using mathematical induction, this is differ from the previous 3 problems because this is one relation. N factorial is greater than or equal to 2 power n plus 1, but n starts from 5, 6, etc. So here, let p of n be a proportion that n factorial is greater than or equal to 2 power n plus 1. So here the n value starts from 5. So in this basis step, we are going to verify p of 5 is true, not p of 1 is true. Is it clear? Okay. So p of 5 means here we replacing n is 5. So 5 factorial means 120. So which is greater than or equal to 2 power 6. So 2 power 6 means, that means we substituting n is equal to 5. It is a 64, which is also what? 2 power 5 plus 1. This is also 5 factorial. So therefore p of 5 is true. So in this inductive step, assume that p of k is true. So to prove that p of k plus 1 is true. So we consider here to get this p of k plus 1 is true, just we multiplying k plus 1 on both sides. Because if you are going to multiply k plus 1, here means k factorial into k plus 1 into k factorial. We can write it as, I think, k plus 1 whole factorial. So for that, just we multiplying k plus 1 on both sides. So in the next step, actually 2 is less than k plus 1 because k is greater than or equal to 5. So we can write it as in this step, actually in the previous step here we having k plus 1. So for that here we putting a 2 because of this. So k plus 1 whole factorial is greater than or equal to 2 power k plus 2. Therefore p of k plus 1 is true. That's all. So now we move to the fifth problem. 2 power n. Actually, it's like the previous problem. It is a relation form. 2 power n is less than n factorial. But here n starts from 4. It means n is greater than or equal to 4. So we consider the statement is p of n. So in the basis step, we are going to take n is 4. It means p of 4 is true. So 2 power 4 is 16. So this side 4 factorial is 24. So in both sides we're getting 16 is less than 24. Therefore p of 4 is true. So in this inductive step, assume that p of k is 2 power k is less than k factorial is 2. To prove that p of k plus 1 is true. So to prove this, just we multiplying k plus 1 on both sides. So we're getting this k plus 1 2 power k is less than k plus 1 into k factorial. Actually k plus 1 k factorial means we can write it as k plus 1 whole factorial. We are applying the same concept. Here 2 is less, k is greater than or equal to 4. So definitely we say that 2 is less than k plus 1. So in here, instead of this k plus 1, here we putting 2. So we can combine 2 power k plus 1 is less than k plus 1 whole factorial. So automatically we say that p of k plus 1 is true. So by using the principle of mathematical induction, we prove the given one. 2 power n is less than n factorial. This is the sixth problem. Prove that for every positive integer 1 plus 1 by root 2, 1 by root 3, etc. plus 1 by root n is greater than 2 times root of n plus 1 minus 1. So here's the entirely different problem. Solution. Let P of n be a proportion that 1 plus 1 by 2 etc. This is the given one where n is a positive integer. So in this basis step, as usual, we taking n is equal to 1 because here no conditions are no conditions for n. So here, so as usual, we take n is equal to 1. So P of 1 is equal to, so here 1 by root of 1, it means 1. So this 1 is greater than, so here in this right hand side, we substituting n is equal to 1 and simplifying, we're getting 0.828. So obviously we say that 1 is greater than this. So therefore P of 1 is true. In step 2, we consider P of k is true. So here just we putting n is equal to k. Okay, so P of k is, as the assumption is over. So using this assumption, we are going to prove P of k plus 1 is true. So here, to get the result, just we adding 1 by root of k plus 1. So why we are going to add 1 by root of k plus 1? Because the last term of the previous step is 1 by root k. So here we adding 1 by root of k plus 1 on both sides. We getting this and this 2 into just we cross multiplying this 2 into minus 1, we write it here. Then after that we combine this and this. Combine means just we cross multiplying, we getting this. So which is greater than. So 2 into this k plus 1 plus 1 can be written as root of, for example, root 2 into root 2 is 2. So in that way, here we write it as root of k plus 1 plus 1, root of k plus 1 plus 1. So here we're using one concept, k plus 1 plus 2 means k plus 2. And so obviously it's greater than k plus 1. So we can write it as k plus 1 plus 1, which is root of k plus 1. So this root k plus 1 is cancelled. So we're getting 1 by 1 plus 1 by root 2 plus 1 by root 3 plus etc. plus 1 by root k plus 1 is greater than 2 times root of k plus 1 plus 1 minus 1. So hence the proof. So by using principle of mathematical induction, we prove the result. So therefore P of k plus 1 is 2, hence the proof. So these are the 7 and 8 problem or the practice problems. So thank you. Hope everyone understood the topic mathematical induction from Combinatorics Discrete Mathematics. Thank you.